Hi, welcome to the four coins problem, a nice little geometry problem we will solve using inversion. What is the precise problem statement? We have four coins which are circular but might be of different types and sizes, which lie on the table such that each of them is touching two of the neighboring ones. So we want to show that the 4 points, which are the points of tangency in this configuration, are concyclic. So instead of coins, we might be using the word circles, and so this is a nice picture of the situation we are facing. The four circles with the normal line are the coins, and the dashed line is what we shall prove that these 4 points of tangency or 4 points of touching lie on one circle. So let's get into that. Why should we use inversion for such a problem? So inversion is generally a useful tool when you have a lot of circles and when from the lot of circles, many go through one point. Then it makes sense to kind of choose the center of inversion or the center of the circle with respect to which you do the inversion as that point through which many circles go through. Because inversion has such an ability that any circle that goes through its sort of inversion circle center will be transformed into a line. So in this case, if we will invert through x, then this big circle on the bottom left, this circle on the bottom right, and the dashed circle will all turn into lines. So we will transform our problem from a problem about 5 circles to a problem with 3 lines and 2 circles. These 2 circles on the top will remain circles after the inversion as well. So this might seem that whenever you have some circles intersecting, it makes sense to use inversion to make your life easier. But this is not always the case. Please remember then when you have, for example, a problem where you have a triangle and some circles which are intersecting, it is not very wise to use inversion because while those 2 circles might become lines, the sides of the triangle, which are lines not going through that center of inversion, will all become circles. So it always makes sense to kind of count how many lines will become circles and how many circles will become lines. And only if the number of the circles is decreasing, it is a good idea to use inversion. There might be cases when this is not the case, but those are the minority. So for now, let's stick to that rule that if you manage to reduce the number of circles, then it is a good idea to use inversion. And here, this is the case because we take the number of circles from 5 down to 2. So let's see what will happen. If we invert through x, these 2 circles will become lines, and they have no other common point than x. But x in inversion becomes the point at infinity. So these 2 lines, which will be the images of these 2 circles on the bottom, must be parallel because they are not allowed to have an intersection point on the normal plane. Okay, so 2 parallel lines and 2 circles which touch. Each touches one of these lines and they are also touching themselves. Okay, and this circle, this dashed circle, which we actually want to prove that it's a circle, right? It should become a line. So let's see. These are the 2 bottom circles, these are the 2 top circles, and the dashed circle should become a dashed line. So what is this new problem statement? So exactly as I described, the 2 circles go through x, they will turn into lines, and they meet only at the x, which will become the infinity points, so they have no other common points. So therefore, they must be parallel. The upper circles will become these. They will be inverted to different circles which are still touching, and they are also touching one of our new lines each. And the dashed circle should become a line. So now even the problem statement changed. Instead of proving that 4 points lie on a circle, we have to prove that 3 points lie on a line. What happened to the fourth point? The fourth point was x, which got transported or transformed or inverted into this infinity point, right? And through the infinity point, all lines go through. Okay, so in fact, we must prove that this point, this point, this point, so the 3 points of tangency on this picture, and the infinity point lie on a line. But because of the infinity point lies on all the lines, we don't have to worry about it. We only have to prove the collinearity of these 3 points. Okay, so we can notice that even the problem statement becomes inverted by the transformation. Okay, so when using inversion, you almost always have to think about what the problem statement you want to prove becomes. Okay, so now we got a consequently transformed into a collinearity. And so let's see that how would you prove this one. Okay, so this is the new problem statement, and this is simpler problem because we just need to consider this homothety or similarity with the center at the point of tangency of the two circles. We shall call this y, and let's see what the details of this proof are. This might be a simple known fact, so if you are already familiar, feel free to skip the next part of the video. So the details of the solution are as follow. So let us take the homothety with center at y such that the left line is transformed onto the right line. This is just about choosing the right coefficient. Okay, so because y is between the two lines, this will be a similarity with negative coefficient. Okay, so what will be the image of the left circle with this transformation? It must be a circle that touches the right line, right? Because the object, this left circle, was touching the left line. So the image of the circle will be a circle, and it must touch the image of the left line, that is the right line. So it will be a circle that touches the right line, and it also goes through y. There are many such. There are many such circles, but there's more to that because it's not enough that it goes through y, it also must touch the left circle in y. So the right circle, this image, must touch the left circle. Because if you consider the tangent at y to the left circle, so the tangent to the left circle at y, it separates the two circles. Because if you consider it, then if you consider the tangent, the whole of the left circle, the object, is to the right of it. But when you use this similarity with negative coefficient, all of those points will get transformed onto the other half plane, which is defined by that line. So there is not another point that might be an intersection point. So there's only this touching. Okay, so we now know that the image of the left circle will be the right circle because there's only one circle which touches the left circle at y and touches the right lane, the right line. And now we only have to realize that tangency points are each other's images and at this homothety, and because of that they must lie on a line. Okay, and this is simply the truth, and therefore we are done. So here is again the diagram. If you look at this, then the left line will go to the right line, and the left circle will become the right circle. Okay, and so if you think about this y and this tangent for the left circle, so the tangent is such that the whole circle is to the left from this tangent. So any point which is not y, you can just take it and look at its image. It will go through y, so it will be somewhere here. So there's no way that it will be an intersection point because it's already on the other side of the tangent. So no more other common points. So these two circles in fact touch here. Okay. And so we get this left circle because one object and another object have a common point. So the images of these objects will also have a common point. And because we know that this is the only possible circle, we know that this point will become this point at the homothety. So really, these 3 points must lie on a line. And this is what we wanted to prove. If we invert back this statement, which we have now proven, then we will get 4 circles, and that the image of this line with the inversion, which is a circle, will pass through the 4 points of tangency. So that is what we wanted to do. Okay, so now to recap, we had an initial problem which was a bit hard, so we used inversion to simplify it and to transform also the problem statement. Okay, so this was useful because we managed to get rid of some circles, and it's easier to work with lines than it is with circles. So the situation became easier, and we also get a new statement which was easier to prove. Okay, we only needed some properties of similarity, and if we thought about it hard enough, it became clear that this collinearity follows from the properties of similarity. Okay, so this was the problem. Let me know what you think, or if you have any similar problems you would like to see the solution of. Thank you.